Wilhelm Conrad Roentgen, a world-renowned researcher and awardee of the first Nobel Prize in Physics. How did he manage to go to university without a high school diploma? Why didn't he protect his method of X-ray generation with a patent? And why did he deny Prince Regent Luitpold of Bavaria's offer to ennoble him?
March the 27th, 1845. Roentgen is born in the small German town of Lennep, close to Remscheid in North Rhine-Westphalia. He's the only child of the cloth merchant Friedrich Conrad Roentgen and his wife Charlotte Constanze. The family later moves to the Netherlands, which is the mother's country of origin. At the age of 18, Wilhelm's school education there comes to a sudden end due to a caricature of his class teacher, which is falsely attributed to him. Because he refuses to name the actual perpetrator, he gets expelled from school without a diploma. A scientific career seems impossible. But Roentgen is not willing to give up just yet. Even though he's not enrolled, he takes classes at the University of Utrecht. Later, he visits the Federal Polytechnic Institute in Zurich, known today as ETH, where he's allowed to study without a high school diploma thanks to his exceptional skills. At the age of 23, he graduates with a degree in mechanical engineering. 1 year later, he receives his doctorate for the investigation of the volumes and temperatures of gases. In 1869, Roentgen comes to Würzburg for the first time as an unpaid assistant and habilitation candidate. The attempt to achieve this formal qualification for professorship fails due to the missing high school diploma. In private life, he's a bit more lucky and marries Anna Bertha Ludwig, whom he met at her father's restaurant in Zurich, a place he used to visit often as a student. When Roentgen moves to Strasbourg as a lecturer, the tide is also turning for him professionally. Upon special request, he finally achieves his habilitation. Following a few other positions, he ends up in Gießen in 1879. After some time-consuming and tedious experiments, he succeeds in confirming a theory by James Clerk Maxwell. By demonstrating the existence of a so-called displacement current, he achieves a milestone in electrodynamics and receives worldwide attention as a renowned physicist. This same year, he decides to move back to Würzburg because the lab in Gießen wasn't big enough anymore.
The Institute of Physics at the University of Würzburg. Roentgen returns to a modern laboratory with world-class facilities, much different than those during his years as an assistant. Supplemented with some of his own devices, the equipment will soon enable some of his groundbreaking observations. However, his greatest discovery is, next to Roentgen's tenacity, owed to a coincidence, as is often the case in science. On November 8, 1895, the physicist works late. It is the time of rapid industrialization in Europe. The railroad industry is booming and towns are equipped with electricity. Modern communication is established, such as the telephone. This progress comes at a high cost. People work an average of 70 hours per week, and rooms frequently have up to 5 or more occupants due to a lack of housing. In his lab, Roentgen is investigating the properties of gas discharge with cathode ray tubes. It is known that this phenomenon causes the tube to light up inside. Roentgen tries out different tubes, materials, and voltages. During this experiment on November 8, 1895, he sees something shimmering outside the vacuum tube on a fluorescent screen at increased voltage. He systematically goes into the matter, turning off all the visible light in the lab and covering the tube with black cardboard. The fluorescence on the platinum cyanide screen remains, no matter where it is placed with respect to the tube. From this phenomenon, Roentgen concludes that there must be an unknown kind of radiation, which he calls X-rays, one of the finest hours of science.
But what happened? In those vacuum tubes, electrons are accelerated from cathode to anode by a high voltage. During their passage, they excite gas molecules in the tube to give light. But when reaching the anode, the fast electrons are suddenly decelerated and deflected, forcing them to release energy in the form of then unknown radiation which can penetrate materials. Wilhelm Conrad Roentgen immediately realizes the far-reaching consequences of his observations. He doesn't tell anyone, hides out in his lab for weeks to scrutinize the properties of this radiation. Bulky books, metal foil, wood, nothing can stop the mysterious X-rays, not even the human body. The oldest documented X-ray image is a picture of Roentgen's wife's hand, which was exposed for 15 minutes. When Roentgen is finally confident enough in his observations, the associated publication can't come quick enough. He sends special prints of his article on a new kind of rays to colleagues and friends, and soon newspapers from Berlin, Vienna and around the globe report on his groundbreaking discovery.
The emerging interest in his person makes Roentgen feel increasingly uncomfortable. In the beginning of 1896, he holds his first and only oral presentation of the new radiation. Afterwards, the anatomist, Professor Albert Koelliker, who is present as one of the listeners, suggests to call the X-rays Roentgen radiation. The audience applauds this proposal with standing ovations. In private life, however, Roentgen is indeed a social type. Whenever work allows, he leaves his lab in order to go on vacation with friends for hiking or hunting. Luxury, in contrast, is not for him. He hesitates to enter expensive hotels and will only do it for the sake of his wife, whose health is not at its best. Also, as a professional, Roentgen is humble. He does not apply for a patent for the generation of X-ray radiation. He wants everybody to benefit from his discovery. Some react with mockery and incomprehension, such as the inventor and businessman Thomas Edison. Likewise, Roentgen isn't flattered by honors and medals, culminating in the denial of being ennobled by the Prince Regent Luitpold, which evokes astonishment and also resentment at the ministry in Munich. However, there is one honor that Roentgen appreciates and accepts. In 1901, he is awarded the first Nobel Prize in Physics. The ceremony requires a trip to Stockholm. Roentgen is rather unexcited. In his request to leave, he writes,
"Since these prizes have an exceptionally high value and are very honorable, the deferential obedience Heini believes, though somewhat wary, that he has to adhere to the wishes of the Royal Swedish Academy, therefore requesting vacation for the duration of the coming week."
On the day after the award ceremony, Roentgen already makes his trip back, without giving the customary ceremonial address.
Today, we don't know what was behind his apparent shyness. Roentgen had most of his documentation destroyed after he died, so many things remain unknown or mysterious. For example, it's still unclear why he soon stopped committing himself to a closer investigation of X-ray radiation. In any case, Wilhelm Conrad Roentgen's discovery changed the world. To this day, generations of researchers have developed a multitude of X-ray applications, and their innovations have permeated all aspects of our everyday life.
Non-destructive testing of material properties, determination of the authenticity of art pieces, customs, and medicine. These are just some of the routine applications of X-rays in our everyday life. But what exactly are X-rays?
There are two general types of X-rays which can be distinguished by their origin. So-called Bremsstrahlung is released when charged particles are decelerated. The German term means braking radiation. For example, when an electron moves through the strong electric field of a nucleus, it gets deflected, slows down, and thus loses kinetic energy. This energy is released as radiation, whereby a certain energy range corresponds to X-ray radiation. The second progress generating X-rays is called characteristic radiation. It occurs when electrons play billiards. A particle hits a bound electron in an atom. knocking it off its spot in the atomic shell. The vacancy can only be filled by an electron from a higher shell, that is, with higher energy. In order to fall into the inner shell and fill the spot, the electron has to give up some of its energy and releases it as electromagnetic radiation, the so-called characteristic X-ray radiation.
When Wilhelm Conrad Röntgen published the tremendous properties of this remarkable radiation in 1895, the news spread around the globe like wildfire. However, not everyone was entirely convinced at first. While physicians and natural scientists were extremely excited, some people had reservations about this new radiation that had the capacity to penetrate everything. However, not all of those were completely serious. This caricature displays the fear of body scanners that would bear the seemingly innocent citizens and expose their hearts of stone. On screen, men with X-ray vision made the world unsafe. But there were also real-world doubts about the applications of X-rays. For a long time, people were unaware of their harmfulness. Feet were radiographed in shoe stores to find the perfect fit. At parties, taking X-ray images of limbs was thought of as a fun game, and headaches thereafter were treated with a 15-minute exposure to the supposedly healing X-ray radiation.
Today's applications of X-rays are far more serious, mainly in medicine. Röntgen's discovery revolutionized the examination of bones and tissue. For the first time in history, it was possible to create an image of the inner body of a patient. Nowadays, these pictures are even taken in 3D. For example, it's possible to image a beating heart in order to detect constrictions in a coronary vessel using CT. But there are also many applications beyond the use of X-rays in medicine. In harbours and at border posts, X-rays allow valuable insights. Fully loaded trucks are scanned, so smuggled goods have become way more difficult to hide. In industry, fissures, cracks, holes and trapped air in components compose a high risk to personal safety. X-rays can identify such defective parts quickly and reliably. Historic paintings often consist of several layers because they were painted over again and again. For example, in order to create a counterfeit on a historic canvas, X-ray technology can find the image behind the image.
Widely unknown to the public, one of the most important applications of X-rays is so-called X-ray diffraction. It allows for an examination of matter on an atomic level, and is thus a key method in materials science, but also in molecular biology. We owe the knowledge of DNA structure with its characteristic double helix to this technology. In the pharmaceutical industry, X-ray diffraction helps with the development of new drug substances, for example in cancer research. However, this technology requires substantial effort. Huge particle accelerators like the XFEL near Hamburg are needed. Here, electrons are brought to high speeds of almost the speed of light along a 3.4-kilometer tunnel, producing up to 27,000 X-ray flashes per second. X-ray radiation also assumes a central role in the ongoing miniaturization of microelectronics. The photolithographic production of computer chips, for example for smartphones, uses soft X-ray radiation with wavelengths of a few nanometers.
The largest part of X-ray radiation, however, is of natural origin. In the depths of the universe, it emerges in stellar systems and during supernova. Fortunately, these X-rays do not make it onto the Earth's surface thanks to our atmosphere, which protects our planet from these extraterrestrial impacts. X-ray satellites such as eRosita help scientists to understand this radiation coming from space. The mission, which started in 2019, is investigating the origin of this structure of the universe and exploring the most fascinating questions in astronomy. Researchers hope that the X-ray telescope mission is going to unravel the secrets of the mysterious dark energy and dark matter, find black holes, and help explore distant galaxies.